So, good morning, guys. Thank you all for being here. Again, we are finishing up our trig unit. We are going to start with today, we're going over sine and cosine curves. So, we'll also look at tangent and the other trig functions as well. So, today's all about graphing. The sine curve is a graph of the sine function. One cycle or period is the time it takes to repeat itself. The amplitude is simply the height of the function, and the phase shift is talking about moving it left or right. So, some basics here. For when we're between values of 0 and 2 pi, which is the same as like between 0 and 360 degrees, the sine function has max and mins at 2 pi, pi over 2, comma 1, and a minimum at 3 pi over 2, comma negative 1. That has x-intercepts at 0, 0. Pi, comma 0, 2 pi, comma 0. Cosine over that same range has two maximums actually, one at 0, comma 1, and another at 2 pi, comma 1. So that's where it kind of starts repeating itself, just like 0 to 0, or 0, comma 0 to 2 pi, comma 0 in the sine function. This has a minimum at pi, comma negative 1, and x-intercepts where the max and mins were for sine. So at pi over 2 and 3 pi over 2 are zeros for the cosine function. Leave the first one here. Yep. Sketch the basic function. So before we actually sketch it out together, we're going to look at it on Desmos. So we have, I think my screen share is a little off. Oh, wow. Sorry about that. That was so quickly for those who were online. I am sorry my screen share was off before. So here you just kind of saw me talk or just heard me talking without these notes, but just very quickly, again, these are my max and mins. And again, we have our vocabulary definitions here. Again, one cycle, we'll also call that the period, how long it takes to repeat itself. The height is the same as the amplitude, and phase shift is moving left and right. So, there we go. There's the Desmos. So if I hit play on this, let's see what happens. I start getting functions that are made here. Notice they're actually pretty neat looking curves. So they're nice and clean. One is sine, one is cosine. The green is our sine curve. The orange is our cosine curve. I'm going to let it go through again. If we look closely, the height of the green line is the same as the height of the green curve. We'll see that in action in a moment. And again, the width of the orange line is actually the height of the orange curve. So I'm actually going to pause this and we'll look at some of the critical points. So let me get that almost all the way done. There we go. So like here would be a max. Here would be a min. That's for the sine curve. So if I go back and look at the notes, when I say, what's the max and min of my sine curve? There we go. We see that they match exactly. If I were to click on my x-intercepts, I'm not all the way there on that one yet. But again, my x-intercept seems to match up. I start clicking on cosine, I again see similar information matching up. So what I want to do now is I'm just going to we see this green horizontal line. That's the same as what's going to be the green vertical line. And we'll see that it helps us on this curve. The orange, what I just added, this orange line is actually the same as the orange line over here. And then again, we'll have that to track its height to the cosine curve. Actually, let me go projector mode on this, so it's a little bigger for us to see. So let's look at this again. Notice that it's really sticking to these horizontal lines I just recently added are basically showing us where our curve is. So again, we see the green all match up and the orange, even though, let me pause it midway through where I can see the orange line pretty good. There we go. We notice this orange line, let me use the mouse, or the orange horizontal line here as part of the triangle, that's the same length as this vertical line at 2. And again, we see that these horizontal lines are keep tracking the height. So basically, it all comes down to the unit circle, and the unit circle is creating these. So those values I'm asking you to memorize off the unit circle will actually dictate a lot of that, or all of this. So now that we've seen them in action, let's just sketch the basic curve. So for sine, remember my critical points are, looks like this is off a little bit. Let me get that fixed. Are going to be where sine starts, 0, 0. That goes up to pi over 2, 1. So like if I were to make a table like so with my x and then my sine of x values, I'd start at 0, go to pi over 2, pi, 3 pi over 2, and 2 pi. So sine starts at 0, goes up to 1, goes back to 0 at pi, -1 at 3 pi over 2, and back to 0. So here's how I will scale my axes. I'm just going to say pi over 2, pi, 3 pi over 2, and then 2 pi. So I use my x values up here to scale my x-axis. Now it's just a matter of plotting the points. 0, 0, 2 pi, or pi over 2, 1, pi, 0, 3 pi over 2, -1, and 2 pi, 0. So that gives me a nice, smooth wave function through these points. So that is our sine graph. If I am going to change things about it, this is my default, that we can just manipulate these points. And we'll look at how to do that in a moment. Cosine is the same idea, except cosine just has different return values. So again, I want to start at 0, pi over 2, pi, 3 pi over 2, and 2 pi. So if I look at the unit circle, my x value, or my horizontal value, when x is equal to 0 is 1. Then it goes at pi over 2, it's 0. At negative pi, I get to, or sorry, at pi, I get to -1. At 3 pi over 2, I'm at 0. And at 2 pi, I return to 1. So my period again is 2 pi. Just like again, I went 0 up to 1, back to 0, down to 1, back up to 0. Yeah, it just repeats itself. That's what I mean when I say, hey, the period's 2 pi. Hey, once I get back to 2 pi, I'm back to where I started. Yeah, these are highly repetitive, and that's the point. So pi over 2, pi, 3 pi over 2, and 2 pi. So again, this one starts up here now, goes to here, down here, here, and back up. So this curve literally is just shifted from the previous one. Actually, that was a little sloppy of me drawing. Let me draw a better one. There we go. So literally, as we had seen before, in Desmos, they're just shifted from one another. So here with this, if I put a number in front of A, it makes it taller or shorter. Basically, it just changes the height if I put something in front. So if the absolute value of A is greater than 1, it makes it taller. If the absolute value is between 0 and 1, it makes it shorter. So the range will always be between negative and positive A, where A is the coefficient on our sine or cosine function, instead of being between -1 and +1. That A value will also be considered the amplitude. So by default, this has an amplitude of 1 because at my base, I'm at 0, then I go up or down to -1 or +1. And that's my amplitude. So if I put a 4 in front of it, my amplitude's now 4. So the graph -0.05 sine of x reflects over the x-axis compared to the other graph. So let's just quickly look at that on Desmos. I can open up a blank graph for us here. So if I was like the sine of x, this is our default graph. If I do -0.5 sine of x, we notice this blue graph gets squished down and actually flips upside down. When the red graph's going up, the blue graph's actually going down. When the blue graph's going up, the red's now going down. So here it not only squished it, cut that amplitude in half compared to before, but it also flipped it over the x-axis because of that negative in front. So here with this, now we're going to talk about the period. The period's a little tougher to calculate. The period, it doesn't matter if we're using sine or cosine. If I had the cosine of bx, the period will now be 2 pi divided by b, or 1 over b times 2 pi over 1. It depends how you want to look at it. So we're going to have two things happen. We can stretch it out horizontally, or we can compress it horizontally. So if b is greater than 1, that means the sine of x, the period, sorry, is less than 2 pi, which will be a horizontal compression. So if I put a big number in here like 5, that says I want to go 5 times faster, essentially. So it's going to compress it horizontally because I move through my curve at 5 times the speed. Whereas if I have a number between 0 and 1, that's going to stretch it horizontally because I'm saying like, hey, I want to slow down by half, so it will take twice as long to go through my curve. So here with this, we're going to find the amplitude of this and then try and graph it, and period. So the amplitude is easy. Amplitude is just equal to 4. Now the period is a little bit trickier. The period, since that has a value of 3, is going to be 1 over 3 times 2 pi over 1. So really my period now becomes 2 pi over 3. So we're going to compare this to a regular cosine graph in a minute. I'm going to show us how we get all our important information here. Amplitude had that -4 in front. That's very easy to deal with. It's that period that's going to mess us up a little bit more. So my default cosine is x, and then I know cosine. So that would be 0, pi over 2. Too quick there. Pi, 3 pi over 2, and then 2 pi. That gives me now values. I'm at 1, 0, -1, 0, back to 1. Okay. Now the blue is easy. The amplitude is just -4. I'm going to do -4 times everything here. The amplitude will always actually just be the absolute value because we're talking about the height. So even though it says -4 there, I'm going to call the amplitude 4 because the height's 4. The negative's doing just the reflecting over the x-axis. So I'm actually going to multiply by -4 here. So to get my new graph, I'm going to multiply each of these by -4. But I also have the manipulation inside with the bx. So I notice here, since my b value inside the function is 3, it changed the period to 2 pi over 3. I like writing it as 1 over b because it made it very obvious. I did 1/3 times 2 pi. So I actually, since this says 3x inside, I'm going to multiply each of these by 1/3. Times 1/3. So this gives me a brand new table. So if I know I have x times -4 cosine of 3x, here's how it looks now. 0 times 1/3, 0. 1 times -4, -4. This is going to be pi over 6, comma 0. This will be pi over 3, comma +4. This one will be, 3 pi over 6 ends up just reducing to pi over 2, comma 0. And then this ends up being 2 pi over 3, comma -4. So those are my new critical values. So let's take a look at these in Desmos compared. So we had the cosine of x Whoop. There we go. Now we had -4 times the cosine of 3x. So we notice this blue graph. Here would be my critical points. So there's my first period. Critical points from the first period are 0, -4, pi over 6, 0, pi over 3, 4, pi over 2, 0, 2/3 or 2 pi over 3, -4. Same values I listed here. I got it without even graphing. And then we see, again, those critical values. It helps us see now. This appears to go like 3 times faster, the blue, right? I'm going a lot faster through my sine curve compared to the slower curve of the green. Any questions about that? I'm not seeing any looks on faces here or in the chat. I just want to make sure. So here with this, a horizontal shift will be something either added or subtracted inside of there. So that could also be called a phase shift. Essentially what can happen is if we shift a sine function far enough in one direction to the left or right, we can actually get it to look like a cosine function. The easiest way to do that actually is just to shift it pi over 2 radians to the left, and then all of a sudden sine becomes cosine. So yeah, they're talking about how we can shift there. We're going to actually see that happening right here. So the phase shift is just how much it moves left or right. So here with this, my amplitude equals 2. Now my period, it just has x in there, right? There's nothing being multiplied by x. So my period actually remains the same. Period still just 2 pi. And then my phase shift. So if it's being subtracted, remember when we talked about in chapter 1, translations of functions, if it's plus, that's actually going to the right. If it's minus, it's going to the left. So this just moves right by pi over 4. So now we're going to find our new critical points here. So again, my default for sine, I did x sine of x, that's going to be 0, pi over 2, pi, 3 pi over 2, 2 pi, 0, 1, 0, -1, back to 0. So now my new one, my amplitude, I want to double everything on the bottom, and then my period says pi minus 4, or sorry, x over pi over 4. So what we're going to do is we need to move each of these points to the right. Moving them to the right will actually be adding pi over 4 to each of them. So that's what we're going to do. So each of these gets plus a pi over 4. I'm just going to do my math real quick on that. All I'm doing is getting common denominators when I add them. So common denominator is going to be 4 for all of these. And then here, this is really easy, just everything times 2. So that's going to give me a new graph of x comma, so 2 sine of x minus pi over 4. So 0 plus pi over 4 is just pi over 4, comma 0. Then let's see, that's going to be 3 pi over 4, comma 2. Then if I add pi over 4 to pi, that's 5 pi over 4, comma 0. Then here, 3 pi over 2 plus 4 pi, that's going to be, or pi over 4, 7 pi over 4. And finally, I'll have 9 pi over 4 here. So that's -2 and 0. So those are my critical values for this graph. Again, if I very quickly graph this on Desmos, do sine of x, that's my default graph. I said 2 times the sine of x minus pi over 4. So I notice here, my blue graph looks a little odd because it's shifted over. But if I click on here, all those are the same critical values I had before. So look, pi over 4 comma 0, 3 pi over 4 comma 2, all that. That's the same table right here by just clicking on my max and mins. So look, here's a little cheat for you guys. If you're having a little trouble with it right now, you can graph it in Desmos. And you can click on your zeros and your max and mins, and it will tell us our 5 critical points within inside the period. Yes, I showed you all how to do it mathematically, and that's where my focus is. But there's a little shortcut for you. Okay, vertical shifts, all you're doing is adding something to the end. That's really easy. So like if I say a plus 5, let's do it to this. The center line is just going to move up 5. So we notice it kind of has that balancing center line. That just moves up to 5 because if I put y equals 5 here, all of a sudden those critical points we saw before are literally just shifted up 5 units. So here with this, we're going to skip this one, but just for time's sake, so I do want to talk about some of my other functions. Here are some real life situations that these apply to. We're talking about weather and temperature over time. That tends to fit sine and cosine functions very well. Cycles of the moon, again, fit sine and cosine functions very neatly. Springs. When we talk about the motion of like if I had a spring and I pulled it down and let it go, it keeps oscillating up and down. Springs follow straight curves beautifully. The tides, as the tide goes in and out, that follows sine and cosine curves. Sound and light waves, they're waves. They follow these wave functions beautifully. Again, with this, let's see, I can quickly go over this. Let's see, my center line's at 2, because I go from 2 up to 4, back down to 2, down to 0, up to 2. So 2 seems to be where I'm centering. So I will have a +2. Let's see, my period's still 2 pi, so I don't have to worry about that. My amplitude seems to be 2 because I go from 2 up to 4, so that goes up by 2 units. So let's see, I started at my center line, so that will be sine of x. If I started at a max or a min, that would be cosine. So homework, there is, I think I left you some of the homework problems done inside the notes, so there you go. Very quickly, I want to talk about some other functions. Do not have homework with this, but we're just going to run through as much of these notes as we can. So the tangent function is an odd function. It is symmetric with respect to the origin. It has tangent, or the period of a tangent function is pi. The tangent function has vertical asymptotes at pi over 2 plus n pi. So I have multiple vertical asymptotes. So tangent looks like so. Let's delete these. The tangent of x looks like this. And if I started like pi over 2, it said is where one of my asymptotes is. Well, x equals, sorry. So there's one of my vertical asymptotes. If I were to add n pi to it, so if I add pi, so like if I said x equals 3 pi over 2, again, I get another vertical asymptote. If I went the other way and went negative, x equals negative pi over 2, I get another vertical asymptote. So that's what's kind of special about tangent. Not going to focus as much on the graphs of tangents, just let you be exposed to it. So here's our default table for tangent. At pi over, or at negative pi over 2, it's undefined. At negative pi over 4, it's negative 1. Then we got 0, 0. At pi over 4, it's positive 1. And then at pi over 2, it becomes undefined again. So again, if I put something in front of it, A will affect the y value by multiplying it. B affects the period in the same way it worked with sine and cosine functions. But now instead of being 2 pi for the period, it's just pi. And then C will move it left and right. So cotangent looks the same, it's just shifted over. So if I look at cotangent compared to tangent, we see this happening. You know, let me turn off the tangent for right now. It kind of reflects it around and shifts it over. So watch this. If I did the tangent of negative x, we start to see that go in the same way. And then I need to move it at, doesn't matter left or right. How many units? Pi over 2. No. Or no, pi. I need to shift it 1. No, pi over 2, half a phase. So I can be like, oh, plus pi over 2. And all of a sudden, tangent and cotangent become the same graph. So our reciprocal functions, they look a little weird. Basically, they are alternating parabolas between asymptotes. I'll show you what that means. So like if I have sine of x, or let's start with cosecant of x, that looks like this. This looks really weird right now. But if I put in sine of x with this, we actually see wherever like a max was, that gives me this parabola that's flipped upside down or flipped right side up. Wherever a min was, it just flipped upside down as a parabola. And again, if I go with any of my x-intercepts, like say pi, if I said, oh, x equals pi, I get this vertical asymptote happening. So again, I'm just trying to expose you to these functions. Not giving you a ton of homework on these or anything like that. So cosine and secant work the same way. Again, we can talk about their domain and range. They're a little more tricky. You can read that in the notes. But basically, because the range of sine and cosine was between between -1 and +1. Now, when we do the reciprocal functions, it flips. Instead of being between -1 and +1, it's now y has to be bigger than 1 or smaller than -1. So those are just flipped. So to draw those curves, we will draw both positive and negative parabolas between the asymptotes. And basically, again, we can talk about that. Those valleys and hills will be reversed. So I'm going uphill here. That actually goes down as my parabola. Here is where I'm going downhill. This actually goes up as my parabola. So that is the basics of these functions. Look, sine, cosine is where I want us to focus. You guys, what I'm going to say for the homework for 4.6 is literally just play with tangent, cotangent, secant, and cosecant graphs and Desmos, and just learn about them through playing, not assigning formal homework with 4.6, just 4.5 with the sine and cosine graphs. So that is what I have for today. Thank you guys for being here. Please do not log off just yet. Stop recording.